For most of human history, the night sky appeared close, almost intimate, as if the stars were stitched into a dome just beyond reach. They rose and set with predictable rhythm, guiding travelers, shaping myths, and anchoring calendars. They felt permanent, fixed, and strangely nearby, even though no one could ever touch them. The sky was not perceived as a place with depth, but as a surface, beautiful and mysterious, yet fundamentally flat. Tonight, we will begin exploring how a single idea transformed that flat ceiling of lights into a vast, layered universe filled with distance, history, and time itself. Before that transformation, distance was understood through effort. How long it took to walk somewhere. How many days a journey required. How far a voice could carry. Even oceans, immense as they were, could be crossed with enough patience. Space offered no such intuition. There were no paths between stars, no visible markers to suggest how far away one point of light might be from another. Without a shared frame of reference, the cosmos resisted measurement. Early astronomers could map the sky with remarkable precision. They tracked planetary motions, predicted eclipses, and cataloged stars with astonishing care. Yet despite this sophistication, they had no reliable way to determine how far away those stars actually were. A star's brightness might suggest closeness, but brightness could also mean size. Without knowing how luminous a star truly was, distance remained guesswork. This limitation shaped how the universe was imagined. Stars were not places, they were symbols. They represented gods, heroes, and seasons rather than locations separated by immense voids. Even when thinkers proposed that stars were distant suns, the idea was philosophical rather than measurable. There was no ruler long enough to stretch across the heavens. The turning point came not from building a larger ruler, but from realizing that the universe already had one built into its structure. That ruler was light. Light had always been central to observation, but for centuries its nature was misunderstood. Some believed it moved instantly. Others suspected it traveled extremely fast, but still had speed. The debate persisted until careful observation finally proved that light does not arrive all at once. It moves, and it moves at a constant, measurable rate. This realization carried unexpected consequences. If light takes time to travel, then seeing something far away is not the same as seeing it as it exists now. Observation became an act of looking backward. Distance and time, once treated as separate concepts, fused into a single relationship governed by the motion of light through space. The speed itself is difficult to grasp. Light travels nearly 300,000 kilometers every second. In that time, it can circle Earth multiple times. In minutes, it bridges the gap between planets. In hours, it leaves the solar system behind. Yet even at this speed, the universe remains vast beyond intuition. Astronomers quickly encountered a problem. Using kilometers to describe interstellar distances produced numbers so large they became meaningless. Writing them down did not help understanding. The universe demanded a unit that matched its scale and its physics, not human travel. That is why the light year was born. A light year is the distance light travels in 1 year. Nothing more, nothing less. It is not a measure of time, despite the name. It is a measure of separation defined by motion, linking space to duration in a way no previous unit ever had. In 1 year, light travels about 9.46 trillion kilometers. The number itself is not the important part. What matters is what it represents. A star 1 light-year away is seen as it was 1 year ago. A star 10 light-years away is observed a decade in the past. Distance becomes history. With this single concept, the universe changed character. The night sky was no longer a collection of distant lights existing simultaneously. It became a layered record of different moments in time. Nearby stars showed recent history. Distant stars preserved ancient states. The farther the gaze, the older the light. This was not just a scientific shift, but a philosophical one. The present moment lost its dominance. What we see is never now in the cosmic sense. It is always delayed, filtered through time spent traveling across emptiness. The nearest star system to Earth, Alpha Centauri, lies just over 4 light-years away. The light entering telescopes today left those stars more than 4 years ago. Any change occurring there right now remains invisible, moving toward us at light speed, indifferent to attention or anticipation. Within our own galaxy, the implications expand dramatically. The Milky Way spans roughly 100,000 light-years. Light from stars near its far edge began traveling toward Earth long before recorded history. When astronomers observe those regions, they are studying conditions that existed when early humans were just beginning to shape tools and language. Beyond the Milky Way, entire galaxies appear millions or billions of light-years away. Their light carries information from epochs when Earth did not yet exist, when stars were forming differently, when the universe itself was younger, denser, and less structured. Telescopes became something more than instruments of magnification. They became tools for archaeology on a cosmic scale. Each improvement in sensitivity allowed astronomers to see deeper, not just into space, but into time. The universe revealed itself gradually, layer by layer, photon by photon. This understanding also introduced limits. No matter how advanced technology becomes, no signal can outrun light. Information travels at a fixed pace. Events unfold, but their effects propagate outward slowly, bound by the geometry of space-time. The universe enforces patience at every scale. Even the sun demonstrates this principle. Sunlight takes about 8 minutes to reach Earth. The warmth felt on your skin is already minutes old. If the sun were to change suddenly, Earth would continue receiving light as if nothing had happened, unaware of the shift until the delay elapsed. The light year simply extends this everyday delay to its ultimate expression. It reminds us that immediacy is local, not universal. As astronomers pushed their observations farther, they discovered that the universe itself is expanding. This expansion complicates distance further, stretching space while light is still in transit. Some galaxies appear to be farther away than light could have traveled in the age of the universe if space were static. The light year remains the anchor that makes these ideas intelligible, even when intuition fails. There is also a boundary created by this relationship. The observable universe is defined not by an edge in space, but by how far light has had time to travel since cosmic expansion began. Beyond that horizon, light has not yet arrived, and perhaps never will. This does not imply emptiness beyond, only separation enforced by time and expansion. The universe may extend far beyond what can ever be observed. The light year marks the limits of knowledge, not existence. Understanding the light year also reshapes how discoveries are communicated. When astronomers announce a new planet hundreds of light years away, they implicitly acknowledge uncertainty. The planet exists, but its present condition is unknown. What is observed is a snapshot preserved by distance. There is a quiet humility in this. The universe does not reveal itself all at once. It speaks slowly, through light that has traveled immense distances without interruption. Every observation is a message sent long before there was anyone to receive it. If this exploration sparks curiosity, and if you find yourself drawn to how these ideas unfold over time, a gentle way to support this work is simply to stay connected. Subscribing allows these longer, deeper explorations to continue, reaching others who are equally curious about how the universe tells its story. In the chapters ahead, this idea of distance will deepen. The light year will stop feeling abstract and begin to feel structural, shaping how stars live, how galaxies evolve, and how the universe reveals its past. To understand the light year fully, we must first understand the thing that defines it. That brings us to light itself. When light became a clock, long before light became a ruler, it was simply a messenger. It revealed shape, color, and motion, but its own nature remained elusive. People used light without questioning how it arrived or how long it took. It was assumed to be instantaneous, a bridge without duration. This assumption began to crumble as observation grew more precise. Astronomers noticed subtle delays in celestial events, small discrepancies that could not be explained if light arrived instantly. These delays hinted at motion, at travel, at a finite journey unfolding between source and observer. The first convincing measurements of light speed came not from stars, but from their shadows. Observations of Jupiter's moons revealed timing shifts depending on Earth's position in its orbit. When Earth moved farther from Jupiter, eclipses appeared delayed. When Earth moved closer, they occurred earlier. The only explanation was that light itself required time to cross the changing distance. This discovery carried profound implications. Light was no longer timeless. It became dynamic, moving through space at a constant rate. Once this was accepted, the universe could no longer be thought of as a single, shared moment. Light became a clock. Every beam of light carried a timestamp, marking the moment it left its source. When that light was observed, the observer was not seeing the present state of the object, but its past. Distance became delay, space became history. This redefinition altered the meaning of observation. Looking outward was no longer passive. It was interpretive. Astronomers were no longer asking only what something was, but when the light revealing it had begun its journey. Within the solar system, these delays are small, but measurable. Light from the sun takes minutes. Light from the outer planets takes hours. These intervals already demonstrate that simultaneity is local, not universal. Beyond the solar system, the delays grow enormous. Years pass between emission and observation. Centuries, millennia. The light year formalizes this delay into a unit that unites distance and time into a single expression. Once light was understood as a moving signal, the universe acquired depth. Objects were no longer arranged merely across space, but across eras. Two stars appearing side by side in the sky might belong to vastly different times, separated by millions of years in light travel. This realization dismantled the idea of a universal now. There is no single present moment across the cosmos. Each location exists in its own local present, while observers elsewhere receive delayed information shaped by distance. The night sky, once perceived as a static arrangement, became dynamic. Stars flicker not because they are unstable, but because their light crosses turbulent space. Variations in brightness may reflect changes that occurred long ago, frozen into the light now arriving. Light also preserves change. When a star explodes, its death is not observed everywhere at once. The explosion expands outward at light speed, reaching observers at different times depending on their location. Some civilizations may witness that event long after others have forgotten it ever happened. In this way, the universe becomes asynchronous. Events do not unfold universally. They ripple outward, carried by light like waves on an invisible sea. This property turns light into a historical archive. Photons traveling through space preserve information about temperature, composition, motion, and energy. When they are finally collected by instruments, they deliver messages written long ago. Astronomers learn to read those messages. By splitting light into spectra, they decode chemical signatures. By measuring redshift, they infer motion and expansion. By tracking brightness, they reconstruct stellar life cycles. Each technique depends on the same principle. Light remembers where it came from. The light year frames this memory. It tells scientists how old the information is when it arrives. It allows them to place observations on a timeline, arranging cosmic events into sequences rather than isolated facts. Without this framework, astronomy would collapse into a catalog of disconnected images. With it, the universe becomes a story with continuity, cause, and consequence. Light's role as a clock also introduces boundaries. There are regions of space whose light has not yet reached Earth. There are events that have already occurred but remain unknown because their signals are still in transit. Knowledge is constrained not by intelligence or curiosity, but by geometry and speed. This limitation is not temporary. Some regions are receding faster than light due to cosmic expansion. Their signals will never arrive. They exist beyond communication, separated not by distance alone, but by the structure of space-time itself. Understanding this does not diminish exploration. It defines it. Astronomy becomes the study of what can be known, when it can be known, and what will forever remain beyond reach. As the idea of light as a clock took hold, the light year became more than a convenience. It became a foundational concept, shaping how distance, time, and observation are woven together. In the next chapter, we will explore how astronomers learn to measure these immense distances in practice, transforming abstract units into concrete maps of space, measuring the unmeasurable once light became both ruler and clock. Astronomers faced a new challenge that was just as daunting as the vastness of space itself. Understanding the meaning of a light year was one thing. Actually determining how many light years away an object lay was another entirely. The universe had revealed its scale, but it did not hand over a measuring tape. On Earth, distance can be measured directly. You can stretch a line, pace it out, or use instruments that compare known lengths. In space, none of this is possible. There is no way to travel between stars simply to mark the distance, and even if there were, the journey would take longer than human history. Astronomers had to find methods that worked from a single vantage point, bound to one small planet orbiting an average star. The first breakthrough relied on perspective. Anyone who has held out a finger and alternated, closing one eye and then the other, has seen this effect. The finger appears to shift position against the background. The closer the object, the more noticeable the shift. This simple phenomenon, known as parallax, became the foundation for humanity's first reliable measurements beyond the solar system. As Earth orbits the Sun, its position changes by millions of kilometers over the course of a year. By observing a nearby star from one side of Earth's orbit and then again 6 months later from the opposite side, astronomers could detect a tiny shift in the star's apparent position relative to more distant background stars. That shift was incredibly small, often less than the width of a human hair seen from kilometers away. But it was measurable. This method turned Earth's entire orbit into a baseline. The wider the baseline, the more sensitive the measurement. From that baseline, geometry did the rest. With careful calculation, astronomers could determine how far away a star had to be for its observed shift to match what they saw. This was the first true step into three-dimensional space. Before parallax, the sky was a two-dimensional map. After it, stars gained depth. Some were closer, some farther, and for the first time, those distances were not guesses. They were measurements. Yet parallax had limits. Even the nearest stars show only the faintest shifts. Beyond a few hundred light years, the movement becomes too small to detect with traditional instruments. Space remained vast, and most of it still lay beyond direct measurement. To move farther, astronomers had to become indirect. They began to rely on objects whose intrinsic properties were understood well enough to serve as benchmarks. If you know how bright something truly is, and you can measure how bright it appears from Earth, you can infer how far away it must be. This principle is simple, but applying it required deep understanding of stellar behavior. Certain types of stars proved especially useful. Among them were Cepheid variable stars, whose brightness rises and falls in a regular pattern. Crucially, the period of that variation is directly related to the star's true luminosity. Measure the timing of the pulses, and you know how bright the star really is. Compare that to how bright it appears, and distance follows. These stars became cosmic signposts. Using Cepheid variables, astronomers pushed beyond the reach of parallax, measuring distances to nearby galaxies. The universe expanded again, not physically, but conceptually. What once seemed like isolated star systems were revealed to be vast, separate islands of stars, each containing billions of suns. With each new rung added to what became known as the cosmic distance ladder, the light year became more than a theoretical unit. It became a working tool, applied again and again, extending human knowledge outward. But every rung depended on those below it. Parallax anchored the system. Stellar behavior built upon that foundation. If any step was misunderstood, errors would propagate outward, distorting the entire picture. This made astronomy a discipline of careful calibration. Distances were refined repeatedly as instruments improved and models grew more accurate. The light year itself never changed, but the universe mapped in light years became sharper, more detailed, and more reliable. As observations reached even farther, astronomers encountered galaxies too distant for Cepheid stars to be resolved. New methods were needed. Entire galaxies began to serve as distance markers. Their properties averaged and compared across vast samples. One of the most powerful tools emerged from a discovery that would reshape cosmology. The relationship between a galaxy's distance and the stretching of its light. As space expands, light traveling through it is stretched, shifting toward longer wavelengths. This redshift can be measured precisely. The greater the shift, the farther the light has traveled, and the longer it has been on its journey. By correlating redshift with distance, astronomers gained a new way to measure scales that dwarfed all previous methods. Here, the light year revealed its deepest role. Distance was no longer just separation. It was evidence of cosmic history unfolding over billions of years. Measuring distance meant measuring how long light had been traveling through an expanding universe. At this scale, precision becomes probabilistic rather than exact. Astronomers speak in ranges, uncertainties, and models. Yet even with these limitations, the framework holds. The universe is not immeasurable. It is structured, layered, and accessible through careful interpretation of light. The challenge of measuring distance also revealed something humbling. Our position in the universe is not privileged. There is no central vantage point from which all distances can be measured easily. Every observer, anywhere in the cosmos, would face the same constraints, bound by local perspective and the finite speed of light. This universality is one of the quiet triumphs of the light year. It does not belong to Earth. It belongs to the structure of space-time itself. Any civilization, anywhere, discovering the speed of light would arrive at a similar unit, linking distance to time in the same unavoidable way. As measurements improved, maps of the cosmos grew richer. Spiral arms of galaxies became clearer. Clusters and superclusters emerged. Voids, vast regions with few galaxies, appeared between filaments of matter. All of it was organized in light years, tens of thousands, millions, and billions of them. The universe began to look less like a random scattering and more like a grand architecture shaped by gravity and expansion. Measuring distance revealed pattern. Pattern suggested process, and process hinted at origin. Yet even as knowledge expanded, the act of measurement remained constrained by light's patience. Every improvement in technique still relied on photons completing journeys that began long before telescopes existed. Astronomy advanced not by speeding up light, but by learning to listen better when it finally arrived. This patience defines the field. Astronomers wait for light that has crossed unimaginable distances. They interpret signals delayed by millions of years. They accept that some answers will never arrive within a human lifetime, or perhaps ever. The light year, then, is not just a unit of distance. It is a reminder of method. It teaches that understanding the universe requires indirect reasoning, careful calibration, and respect for limits imposed by nature itself. As we move forward, the focus will shift from how distances are measured to what those distances contain. Stars, galaxies, and structures exist not just somewhere far away, but at specific depths in time defined by light years. The nearest stars and the first depth of space. Once astronomers learned how to measure distance beyond the sun, the universe did not immediately explode into incomprehensible vastness. Instead, it opened gradually, beginning with the closest stars, those that form the first true layer of depth beyond our solar system. These nearby suns occupy a special place in astronomy, not because they are unique, but because they are the first proof that space is not empty, not flat, and not uniform. The region surrounding the sun, within a few light years, is often called the stellar neighborhood. On cosmic scales, it is vanishingly small. Yet within this narrow sphere lies the transition between familiarity and the unknown. Here, distance stops being theoretical and becomes tangible in the language of light years. The closest known star system, Alpha Centauri, is more than 4 light years away. That distance alone reshaped human intuition. 4 light years means light departing those stars began its journey toward Earth, before many current events on our planet had unfolded. Even the nearest stellar neighbors exist in a different temporal layer. Alpha Centauri is not a single star, but a complex system of 3. 2 sun-like stars orbit each other closely, while a smaller red dwarf, Proxima Centauri, circles at a much greater distance. Proxima, faint and cool compared to the sun, is the closest of them all. Its light takes just over 4 years to reach Earth, making it the nearest star beyond our own. That number may seem modest compared to the scale of the galaxy, but it carries profound implications. If humanity were to send a spacecraft traveling faster than any probe ever built, it would still take tens of thousands of years to cross that distance. The light year reveals not just how far stars are, but how separated stellar systems truly are. Within 10 light years of the Sun, there are only a few dozen stars. Most are red dwarfs, small and dim compared to the Sun. Bright, sun-like stars are relatively rare. This alone challenges long-held assumptions shaped by the night sky, where brightness dominates attention. The stars most visible to the naked eye are not representative of the galaxy as a whole. They are simply the ones close enough or luminous enough for their light to stand out. The stellar neighborhood is quiet, sparse, and unevenly distributed. Stars are not packed tightly together. Vast regions of space lie between them, filled with thin gas, dust, and darkness. Even in this local region, emptiness dominates. The light year gives scale to that emptiness, turning absence into measurable separation. These nearby stars also reveal diversity. Some burn steadily for billions of years. Others flare violently, releasing bursts of energy that can dwarf the Sun's output in moments. Some host planetary systems, others wander alone. Each system exists as an isolated island, its influence limited by distance and time. Understanding this isolation was another conceptual shift. Gravity binds planets to stars and stars to galaxies. But between individual stars, gravity's pull is weak. The distances are simply too large. The light year marks the boundary between influence and independence. As astronomers studied these nearby systems, they also refined their understanding of stellar motion. Stars are not fixed points. They move, orbiting the center of the galaxy, drifting relative to one another. Over thousands and millions of years, the stellar neighborhood changes shape. Stars pass closer, then move away. Constellations slowly deform, their familiar patterns dissolving over time. This motion is usually imperceptible on human timescales, but measured in light years, it becomes meaningful. A star moving at tens of kilometers per second can still take tens of thousands of years to shift noticeably against the background. Distance dampens speed. The light year stretches motion into patience. Nearby stars also serve as laboratories for understanding stellar physics. Because their distances are known more precisely, astronomers can determine their true brightness, mass, and size with greater confidence. These measurements anchor models used to interpret far more distant stars whose properties must be inferred indirectly. In this way, the first few light years beyond the Sun form the foundation of all stellar astronomy. They are the calibration points, the reference stars against which the rest of the universe is measured. Without them, distance estimates farther out would float without anchor. Yet even within this local bubble, the limits of observation remain. Many nearby stars are faint red dwarfs, invisible to the naked eye. Their existence was unknown until telescopes became sensitive enough to detect them. This suggests that even close to home, the universe hides more than it reveals at first glance. The light year teaches this lesson early. Distance does not merely separate objects. It filters what can be seen. Brightness, size, and energy all interact with distance to determine visibility. What appears dominant may simply be closer. What seems rare may simply be distant or dim. The realization that most stars are small and faint reshaped expectations about planetary systems. Around red dwarfs, planets orbit close, completing years in days or weeks. These worlds exist under conditions very different from Earth's. Yet they may be common, perhaps the dominant type of planetary environment in the galaxy. This abundance of nearby but faint stars also emphasizes how misleading perspective can be. The night sky presents a curated view, shaped by human vision. The light year allows astronomers to correct for that bias, revealing the true population of stars regardless of how bright they appear. As distance increases beyond the immediate neighborhood, stars begin to blur together. Individual systems become harder to resolve. The light from many stars blends into a collective glow. The transition from nearby stars to distant stellar populations marks another boundary defined by light years. This boundary is not abrupt, but gradual. At first, stars are distinct points with measurable distances. Then they become statistical groups. Eventually, they merge into galaxies, massive structures whose individual components can no longer be separated without extraordinary resolution. The first few light years thus represent a threshold. They are the last region where the universe can be explored star by star. Beyond them, astronomy becomes the study of populations, trends, and structures rather than individual neighbors. This shift mirrors the growth of scale itself. The light year does not just measure distance outward. It marks transitions in how the universe must be understood. Different distances demand different tools, different assumptions, and different questions. The nearest stars teach humility. Even the closest cosmic neighbors are unreachable with current technology. Even the simplest journeys require patience, measured in centuries or millennia. The universe is not hostile, but it is indifferent to haste. Yet these same distances also provide stability. Stars do not crowd one another. Stellar systems evolve largely undisturbed by their neighbors. Planets enjoy long, stable orbits. Life, if it arises, has time to develop without constant disruption. The light year thus underpins both isolation and continuity. It separates stars while allowing galaxies to persist over billions of years. It creates space for complexity to emerge. As our gaze moves outward, the light year will carry us from these quiet local systems into the crowded structure of the Milky Way itself. There, distance takes on new meaning as stars form patterns, arms, and flows shaped by gravity on a grand scale. Light years inside the Milky Way. As attention moves beyond the nearest stars, the universe begins to organize itself into something larger and more structured. Individual points of light give way to sweeping patterns, and isolation gives way to membership within a vast system. This is where the light year reveals not just separation, but architecture. Within the Milky Way, distance measured in light years becomes the language that explains how billions of stars form a single, coherent galaxy. From Earth, the Milky Way appears as a pale band stretching across the night sky, a faint river of light visible only in dark conditions. For centuries, its nature was debated. Some believed it was a cloud, others imagined it as a collection of distant stars. It was not until telescopes resolved that glow into countless individual points that its true scale began to emerge. The Milky Way is a spiral galaxy, roughly 100,000 light-years across. That number alone transforms perspective. The entire stellar neighborhood explored previously occupies only a tiny fraction of this span. The Sun itself lies about 26,000 light-years from the galactic center, positioned within one of the spiral arms rather than at the core. Even our location within the galaxy is defined by light years. Inside this immense structure, stars are not distributed evenly. They trace spiral arms, vast curving regions where gas and dust are compressed by gravitational waves moving through the galactic disk. These arms are nurseries, places where new stars are born from collapsing clouds. Measuring their shape and spacing requires light years as units, since their full extent dwarfs anything measured in smaller scales. Light years also define motion within the galaxy. Stars orbit the galactic center, completing one revolution over hundreds of millions of years. The Sun's own orbit takes about 225 million years, a journey measured not by distance traveled in kilometers, but by its path traced through tens of thousands of light years of space. Because of this motion, the Milky Way is not static. It rotates, evolves, and reshapes itself slowly. Spiral arms are not fixed structures, but patterns moving through the disk like traffic waves. Stars pass in and out of them over time, born in dense regions and drifting away as they age. Light years allow astronomers to chart these flows, turning the galaxy into a dynamic system rather than a frozen image. Distance within the Milky Way also determines visibility. Dust clouds obscure light, blocking views across large spans of the galactic disk. Even though stars exist on the far side of the galaxy, their light may never reach Earth unaltered. This means the Milky Way cannot be observed all at once from within. Astronomers must piece it together from partial views using radio waves, infrared light, and careful modeling. In this reconstruction, light years serve as both scale and constraint. They define how far signals can travel, how long information takes to arrive, and how regions of the galaxy relate to one another in time. A star exploding on the far side of the Milky Way sends its light toward Earth, but that light may take tens of thousands of years to arrive. By the time it is observed, entire civilizations could have risen and fallen. The galactic center itself lies hidden behind thick curtains of dust. Yet by observing stars orbiting an invisible mass there, astronomers inferred the presence of a supermassive black hole. The motions of those stars, measured across light-year distances, reveal gravity at work on extreme scales. Distance makes mass measurable, turning invisible forces into observable effects. Within the Milky Way, distance also shapes environment. Regions closer to the center are crowded with stars, bathed in radiation, and subject to strong gravitational tides. Farther out, stars are more isolated, moving in calmer orbits. The Sun's position, midway between center and edge, places it in a relatively stable region, one where planetary systems can persist for billions of years. Light years help explain why this matters. A difference of just a few thousand light years inward or outward can change stellar density dramatically. The galaxy is not uniform. It has neighborhoods, gradients, and boundaries, all defined through distance. Beyond the main disk lies the galactic halo, a vast, spherical region extending tens of thousands of light years above and below the plane. Here, ancient stars orbit in random directions, relics from the galaxy's early formation. Their light carries information from epochs long before the Milky Way took its current shape. Measuring these halo stars revealed another surprise. The Milky Way is surrounded by dark matter, an invisible component inferred from the way stars move. Their velocities remain high, even far from the galactic center, suggesting mass distributed well beyond what can be seen. Light years again define the puzzle. The farther out stars are observed, the stronger the evidence becomes. This interplay between light and distance reshaped cosmology. The Milky Way was no longer the entire universe, but one structure among many. Its size, once unimaginable, became a reference point. Other galaxies could be compared, classified, and understood relative to it. Yet even within our own galaxy, the light year remains a reminder of separation. Communication between distant regions is slow. Signals take tens of thousands of years to cross the disk. Events are not shared simultaneously. Different parts of the galaxy exist in different moments relative to one another. This temporal layering means that the Milky Way we observe is already a composite of times. Nearby stars appear closer to the present. Distant regions appear as they were long ago. The galaxy, like the universe itself, is never seen as a single instant. The light year thus becomes the thread connecting structure to history. It tells how the galaxy is shaped, how it moves, and how it changes. It reveals that even within one gravitational system, time and distance are inseparable. As observation pushes beyond the Milky Way, this relationship intensifies. The distances grow from tens of thousands of light years to millions, then billions. The galaxy becomes one island among countless others, separated by oceans of space defined by light's long journey. Crossing the space between galaxies, once the Milky Way is understood as a vast structure stretching 100,000 light years across, a natural assumption follows. With something so large and complex filling the sky, it is tempting to imagine that galaxies sit relatively close together, separated by modest gaps compared to their internal scale. The reality is far more extreme. The light year reveals that galaxies are not neighbors in any familiar sense. They are islands, isolated by distances so large that even their immense sizes feel small by comparison. Leaving the Milky Way is not a gradual transition. It is an abrupt departure from density into emptiness. Beyond the outermost halo of stars, where the galaxy's gravitational influence weakens, space opens into vast regions with almost nothing in them. These intergalactic spaces are not completely empty, but their contents are so sparse that matter becomes difficult to detect at all. The nearest large galaxy to the Milky Way, Andromeda, lies about 2.5 million light-years away. This number alone reshapes intuition. Andromeda is enormous, larger than the Milky Way in some estimates, containing hundreds of billions of stars. Yet despite its size, it appears as a faint smudge to the naked eye, because its light has spent millions of years crossing the void between galaxies. Those photons left Andromeda long before the earliest human ancestors walked upright. They traveled through space without guidance, without deviation, crossing distances that dwarf the entire span of our galaxy. When they finally arrive, they deliver an image of Andromeda as it existed millions of years ago, preserved by distance. This is the fundamental nature of intergalactic observation. Galaxies are not seen as they are now, but as they were when their light began its journey. The farther away a galaxy is, the deeper into the past it is observed. The light year becomes not just a unit of separation, but a timestamp attached to every distant structure. Between galaxies lies what is known as the intergalactic medium. It consists mostly of hydrogen gas, scattered so thinly that it barely registers as matter at all. On average, there may be only a few atoms per cubic meter. Compared to the emptiness of space within galaxies, this is still astonishingly sparse. The light year gives meaning to this sparseness, stretching emptiness across millions of years of travel. Despite this isolation, galaxies are not randomly scattered. They form groups, clusters, and superclusters, arranged along vast filaments that trace the large-scale structure of the universe. These filaments span hundreds of millions of light years, connecting galaxy clusters like threads in a cosmic web. Within a cluster, galaxies may be separated by hundreds of thousands or millions of light years, yet they interact gravitationally. They orbit shared centers of mass, collide, merge, and distort one another over time. These interactions unfold slowly, governed by distances so large that entire galaxies can pass through each other without direct stellar collisions. The light year makes sense of this paradox. Galaxies are dense collections of stars, but stars themselves are separated by light years of space. When galaxies merge, their stars usually pass by one another without contact, while gas clouds collide and compress, triggering new waves of star formation. Distance governs violence as much as proximity. The local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, spans roughly 10 million light-years. Within this region, gravity binds members together, slowly drawing the Milky Way and Andromeda toward an eventual merger billions of years from now. The scale of that event is defined entirely in light-years and time measured in eons. Beyond the local group lie larger clusters such as the Virgo cluster, tens of millions of light-years away. Each cluster contains thousands of galaxies, bound together by gravity and surrounded by halos of dark matter. Light-years define the spacing between these clusters, which can reach hundreds of millions of light-years. At this scale, the universe begins to resemble a vast network rather than a uniform field. Galaxies trace filaments. Filaments intersect at clusters. Between them lie voids, immense regions where few galaxies exist. Some voids span hundreds of millions of light-years, volumes so empty that even intergalactic gas becomes scarce. The discovery of these structures transformed cosmology. The universe was no longer imagined as evenly filled with matter. Instead, matter clumped and stretched into patterns shaped by gravity acting over immense distances. The light year became essential for mapping this architecture, turning abstraction into measurable form. Light traveling through these regions carries subtle signatures of its journey. As it passes through gas, it is absorbed at specific wavelengths. These absorption lines allow astronomers to detect otherwise invisible matter, revealing filaments of gas stretched across intergalactic space. Distance becomes readable through light's interaction with what little matter exists. The further out astronomers look, the more extreme these distances become. Galaxies billions of light-years away appear smaller, fainter, and more distorted. Their light is stretched by cosmic expansion, shifted toward redder wavelengths. The light year here becomes inseparable from the expansion of space itself. At great distances, galaxies no longer resemble the orderly spirals and ellipticals seen nearby. They appear irregular, fragmented, and chaotic. This is not because distant galaxies are inherently disordered, but because they are seen at an earlier stage in cosmic history. The light year turns distance into developmental context. Crossing intergalactic space also highlights a fundamental limit. Even at the speed of light, communication between galaxies is slow. A signal sent from the Milky Way to Andromeda would take millions of years to arrive. Any reply would take just as long. The light year enforces isolation on scales far beyond human experience. This isolation does not imply insignificance. Each galaxy is a universe of stars, planets, and histories. Yet the vast distances between them mean that events in one galaxy have little immediate effect on others. The universe is a collection of largely independent systems, connected by gravity but separated by time. The light year also reshapes how scale is perceived emotionally. Millions and billions of light years challenge the mind's ability to imagine connection. They suggest a universe where closeness is rare and separation is the norm. Even the largest structures are fragile, held together across distances that stretch patience itself. Despite this, the universe remains coherent. Physical laws operate consistently across intergalactic space. Light behaves the same whether it travels a few kilometers or a few billion light years. This consistency allows distant galaxies to be studied with confidence, even when their light began its journey before Earth formed. As observations push farther outward, intergalactic distances grow so large that they approach the limits of what can ever be known. Some galaxies are receding so rapidly due to cosmic expansion that their light will never reach us. They exist beyond the observable universe, permanently separated by distance, measured not just in light years, but in impossibility. This boundary is not marked by an edge or a wall. It is defined by time and expansion, by the fact that light has only had so long to travel. The light year becomes a measure of access, distinguishing what can be seen from what can never be observed. Understanding the space between galaxies clarifies the role of the Milky Way. It is not central. It is not special in position. It is one node among countless others, embedded in a cosmic web defined by distances so vast that even galaxies seem small. The light year thus reframes identity. Earth is not merely far from other stars. It is separated from most of the universe by distances that make interaction impossible. Yet through light, information still flows. The universe speaks slowly across billions of years, and astronomy exists to listen. At this scale, the light year stops being a convenience and becomes a necessity. Without it, the universe dissolves into incomprehensible numbers. With it, even the space between galaxies becomes navigable in thought, mapped through patience and reason. The immensity of intergalactic distance does not end inquiry. It deepens it. Each photon arriving from across the void carries evidence that distance, however vast, can still be crossed by light. Knowledge survives the emptiness. This understanding prepares the ground for the next shift in perspective, where distance becomes inseparable from cosmic history itself, and where looking far enough away means witnessing the universe in its earliest forms, seeing the past through distance. At some point, the idea of distance measured in light years stops feeling like geography and begins to feel like history. The farther outward the universe is observed, the less it resembles the present, and the more it resembles a record of earlier states. Space becomes an archive, and light becomes the medium through which that archive is preserved. This shift is subtle but profound. Nearby stars appear stable and familiar. Distant galaxies look strange, compact, and irregular. At first glance, this might seem like a difference in type, but the light year reveals a deeper truth. These objects are not fundamentally different because of where they are. They are different because of when they are being seen. Every photon arriving at Earth carries information from the moment it was emitted. That moment could be minutes ago, thousands of years ago, or billions of years ago. Distance dictates delay, and delay dictates age. The light year converts separation into chronology. When astronomers observe a galaxy 10 million light years away, they are not seeing that galaxy as it exists now. They are seeing it as it was 10 million years ago. The galaxy may have changed dramatically since then. Stars may have exploded, structures may have shifted, entire regions may have transformed. None of that is visible yet. The light revealing those changes is still traveling. This means the universe never presents a single moment. It presents a layered composition of times, stitched together across the sky. Two galaxies separated by billions of light years may appear side by side in an image, yet represent radically different eras of cosmic history. This effect intensifies with distance. Nearby galaxies appear mature, structured, and well-organized. Farther galaxies look younger, brighter in certain wavelengths, and more chaotic. The light year makes sense of this progression. It shows that structure emerges over time, and distance allows that emergence to be observed. In this way, astronomy becomes a historical science. Unlike geology, which reconstructs the past from remnants, astronomy observes the past directly. The evidence does not need to be inferred. It arrives intact, carried by light that has crossed space uninterrupted. This direct view into the past has reshaped understanding of cosmic evolution. Early galaxies were smaller and more active. Star formation was more intense. Collisions were more frequent. Over billions of years, these systems grew, merged, and settled into the forms seen nearby today. The light year provides the scale needed to place these observations into sequence. Without it, distant galaxies would appear merely different. With it, they become earlier chapters in a continuous story. This temporal layering also explains why the universe looks different depending on where one looks. Observing nearby space reveals stability and maturity. Observing faraway space reveals youth and transformation. The sky becomes a timeline spread across directions. Even individual stars participate in this effect. Massive stars live short lives. They burn brightly and die quickly. When such stars are observed in distant galaxies, they may no longer exist by the time their light arrives. Their deaths have already occurred. But the evidence remains en route. Supernovae illustrate this dramatically. When a star explodes, the flash can briefly outshine an entire galaxy. That explosion expands outward at light speed. Observers at different distances witness the same event at different times. There is no universal moment when the explosion happens everywhere. It unfolds across the universe according to distance. This has practical consequences. Astronomers use distant supernovae as markers to measure cosmic expansion. The brightness and timing of these explosions, observed across vast light-year distances, reveal how the universe has changed over time. Distance becomes data. The farther back astronomers look, the more extreme conditions become. Galaxies observed billions of light years away formed when the universe was denser, hotter, and more compact. Light from that era has been stretched by expansion, shifted into infrared and microwave wavelengths. This stretching carries information. The degree of redshift indicates how much the universe has expanded since the light was emitted. The light year here blends seamlessly with cosmology, linking distance to the growth of space itself. At extreme distances, galaxies begin to fade entirely. Their light becomes so stretched and so faint that it slips beyond detection. This defines a horizon not of space, but of time. Beyond a certain distance, the universe becomes invisible, not because it does not exist, but because its light has not yet arrived or has been stretched beyond recognition. This horizon marks the edge of the observable universe. It is not fixed. As time passes, light from slightly more distant regions may arrive, while other regions recede too quickly to ever be seen. The light year thus defines both opportunity and loss. Understanding this has altered how humanity perceives its cosmic position. Earth does not sit at the center of a static universe. It occupies a moment within an expanding, evolving system. The view from Earth is shaped not by privilege, but by timing. If observers existed elsewhere in the universe, they would see a different past. Their observable universe would include regions hidden from Earth and exclude regions Earth can see. Each vantage point has its own horizon. defined by light years and expansion. This relativity of observation reinforces the idea that no single perspective captures the whole universe. Every observation is partial, delayed, and contextual. The light year does not just measure distance, it measures limitation. Yet within these limits lies extraordinary power. By observing across many distances, astronomers reconstruct sequences of change. They compare nearby and distant galaxies, young and old stars, early and late cosmic environments. Patterns emerge. Laws reveal themselves. The universe becomes intelligible not despite distance, but because of it. The separation enforced by light years creates variation across the sky, and variation allows inference. Without distance, everything would appear the same. With it, time unfolds spatially. This relationship also influences how meaning is assigned to observation. Seeing far does not mean seeing more clearly. It means seeing earlier. The most distant objects are not necessarily the most relevant to present conditions. They are relevant because they reveal origins. The light year, in this sense, functions like depth in an image. Nearby objects provide clarity. Distant objects provide context. Both are necessary for understanding the whole. As instruments improve, astronomers push closer to the universe's earliest moments. They search for the first stars, the first galaxies, the transition from darkness to light. Each success extends observation deeper into time, guided by the same principle: light traveling across space. Eventually, observation reaches a limit. Before a certain epoch, the universe was opaque. Light could not travel freely. Beyond that point, there is no image to collect, only indirect evidence preserved in background radiation. This limit does not end the story, it frames it. The light year defines how far direct observation can reach and where theory must take over. It separates the visible universe from the inferred one. Distance, then, is not an obstacle to understanding. It is the structure through which understanding becomes possible. The light year turns the universe into a narrative stretched across space, where looking outward is an act of remembering. In this framework, every direction in the sky becomes a different window into the past. The universe does not need to be reconstructed from fragments. It presents its history openly, written in light that has traveled patiently across billions of years. The realization that distance equals time is one of the most transformative ideas in science. It replaces immediacy with continuity and replaces isolation with connection across eras. This understanding prepares the way for an even deeper shift, where distance is no longer measured only by how long light travels, but by how space itself stretches that journey, reshaping both light and the universe it reveals. How expansion stretches light. Distance in the universe is not static. It does not behave like the fixed separation between cities on a map. As astronomers began to measure light years across greater and greater scales, they discovered that space itself is changing. The universe is expanding, and that expansion alters the meaning of distance in ways that challenge ordinary intuition. When Edwin Hubble observed that distant galaxies appeared to be moving away from Earth, the initial interpretation seemed straightforward. Galaxies, it was thought, were flying outward through space. But as understanding deepened, a more subtle picture emerged. Galaxies are not simply moving through space. Space itself is stretching, carrying galaxies along with it. This distinction matters profoundly for how light years function. If space were static, a light year would represent a fixed distance traveled by light through an unchanging backdrop. But in an expanding universe, the distance light must cross can grow. while the light is still in transit. The journey itself becomes dynamic. Imagine a photon leaving a distant galaxy billions of years ago. As it begins its journey, the space between that galaxy and Earth is already vast, but as the photon travels, space continues to expand. Increasing the distance still left to cross, the photon moves forward at the speed of light. Yet the path beneath it stretches. This does not prevent the photon from eventually arriving, but it does alter its properties. The expansion of space stretches the wavelength of the light, shifting it toward the red end of the spectrum. This phenomenon is known as cosmological redshift, and it is one of the most important tools for understanding the large-scale universe. Redshift is not caused by motion through space in the ordinary sense. It is caused by the expansion of space itself. The light is not slowed, but its wavelength is elongated as the fabric of the universe expands beneath it. The greater the distance traveled, the greater the stretching. Here, the light year becomes inseparable from cosmic expansion. Distance determines how much the light has been stretched. Stretching reveals how much the universe has expanded since the light was emitted. Measuring one allows inference about the other. This relationship transformed cosmology. By observing the redshift of distant galaxies, astronomers could estimate their distance in light years and reconstruct the history of cosmic expansion. The universe became something that could be measured not just in size, but in growth. At relatively small distances, expansion has little effect. Within galaxies and even clusters of galaxies, gravity dominates. Stars orbit their centers. Galaxies remain bound to one another. Space does not expand noticeably on these scales. Light years here behave much like fixed distances. But beyond these regions, expansion becomes dominant. Galaxies drift apart as space stretches between them. The farther away a galaxy is, the faster it appears to recede. Not because it is moving faster through space, but because there is more expanding space between it and the observer. This leads to a counterintuitive outcome. Some galaxies are so distant that the space between them and Earth is expanding faster than light can cross it. Their light, emitted long ago, may never reach us. These galaxies are not breaking the speed limit of the universe. Instead, they are being carried away by expanding space. The light year here becomes a measure of accessibility rather than simple separation. Some distances can be crossed by light, others cannot. The boundary between these two regimes defines the observable universe. As expansion stretches light, it also alters how the universe appears. Light emitted as visible radiation may arrive as infrared or microwave radiation after billions of years of travel. Observing the distant universe therefore requires instruments sensitive to wavelengths far beyond human vision. This stretching carries information. The amount of redshift tells astronomers how much the universe has expanded during the light's journey. That expansion encodes the influence of gravity, dark matter, and dark energy across cosmic time. The discovery that expansion is accelerating added another layer of complexity. Observations of distant supernovae revealed that galaxies are not just drifting apart, but doing so at an increasing rate. Some unknown influence, labeled dark energy, appears to be driving this acceleration. In an accelerating universe, the future of light years changes. Regions currently observable may eventually slip beyond reach. Light emitted today from sufficiently distant galaxies may never arrive at Earth. The observable universe can shrink in practical terms, even as time moves forward. This makes the present moment cosmically significant. There are photons arriving now that represent the last information we will ever receive from certain regions of space. Once they pass, those regions will fade permanently from view. The expansion of space also means that light years cannot always be interpreted as simple distances. A galaxy observed at a distance of 10 billion light years is not necessarily 10 billion light years away now. The space between has expanded since the light was emitted. The current separation may be much larger. To account for this, astronomers distinguish between different kinds of distance. There is the distance light traveled. There is the distance at the time the light was emitted. And there is the distance now. Each serves a different purpose, and all are expressed in light years, though they describe different aspects of cosmic geometry. This complexity does not weaken the light year. It enriches it. The unit becomes flexible, capable of describing not just static separation, but evolving relationships across time. The expansion of space also reveals something profound about the nature of the universe. There is no central point from which everything expands. Every location observes other galaxies receding. Expansion happens everywhere, uniformly, without preference. From any galaxy, the universe appears the same in this respect. Distance measured in light years behaves consistently, regardless of location. This universality supports the idea that the laws of physics are the same throughout the cosmos. Light traveling through expanding space preserves this uniformity. Its behavior does not depend on direction or destination. A photon emitted billions of years ago obeys the same rules as one emitted moments ago. The light year anchors this consistency across time. Expansion also reframes origin. If the universe is expanding now, then in the past it must have been smaller. Tracing expansion backward leads to an era when all matter and energy were much closer together. The light year becomes a tool for reconstructing this compression, step by step. As astronomers peer deeper into space, they see galaxies closer together, forming rapidly, interacting frequently. The light from these early structures has traveled across immense distances, stretched by expansion into wavelengths that tell the story of cosmic beginnings. Eventually, observation reaches a limit. Before a certain point, the universe was opaque to light. Photons could not travel freely. Beyond that boundary, there is no image to collect. Only relic radiation stretched to microwave wavelengths, filling space almost uniformly. This radiation, the cosmic microwave background, represents the oldest light observable. It has traveled for nearly the entire age of the universe, stretched by expansion from intense heat into a faint glow. Its wavelength carries the imprint of cosmic history written across billions of light years. Here, the light year intersects with the deepest questions of existence. Distance, expansion, and time converge into a single narrative. The universe is not just large. It is dynamic, evolving, and structured by rules that reveal themselves through light's long journey. Understanding how expansion stretches light also clarifies why the universe looks the way it does, why distant galaxies appear redder, why early cosmic structures differ from nearby ones, why there is a horizon beyond which observation fails. The light year ties all of this together. It provides a language for describing motion without movement, change without travel, and separation without edges. It allows the universe to be understood as a system unfolding across time, visible through the steady arrival of stretched light. Expansion does not diminish the meaning of distance. It deepens it. It turns the light year into a record of growth, a measure of how the universe itself has changed while light was on its way. The more deeply this is understood, the clearer it becomes that distance in the universe is not merely about how far away something is. It is about how the universe behaves, how it evolves, and how its history is written into the light that finally reaches us. At this scale, the light year ceases to be a simple unit and becomes a narrative thread, weaving together motion, time, and transformation into a single, coherent picture of the cosmos, the observable universe. At the largest scales imaginable, distance measured in light years stops being a question of how far something is and becomes a question of whether it can ever be known at all. There is a point beyond which the universe does not disappear, but simply becomes unreachable to observation. This boundary is not marked by matter, radiation, or structure. It is marked by time. The observable universe is defined by one simple condition. It includes everything whose light has had enough time to reach us since cosmic expansion began. Nothing more, nothing less. It is not the entire universe. It is the portion that has become visible through the long, patient travel of light. This distinction matters deeply. The universe may be vastly larger than what can be observed, perhaps even infinite. Yet the light year draws a firm, unavoidable line between what can be measured and what must remain speculative. Knowledge is bounded not by intelligence or technology alone, but by the age of the universe and the speed at which information travels. The observable universe has a radius of roughly 46 billion light-years in every direction. At first glance, this number seems impossible. If the universe is about 13.8 billion years old, how can anything be more than 13.8 billion light-years away? The answer lies in expansion. When light began its journey shortly after the universe became transparent, space itself was much smaller. As that light traveled, space expanded, stretching the distance between its source and its destination. The photon did not violate any physical law. It moved at the speed of light through local space. But the space it crossed grew beneath it. This means the distance the light traveled is not the same as the current distance to the source. The light year here becomes layered with meaning. One distance describes how long the light traveled. Another describes how far away the source is now. Both are valid. Both are expressed in light years. Both tell different parts of the same story. The observable universe, then, is not a sphere of fixed size frozen in time. It is a dynamic horizon, shaped by expansion and the passage of time. As the universe ages, light from more distant regions may reach us. At the same time, accelerated expansion ensures that some regions will never become visible, no matter how long we wait. This horizon is not an edge in space. There is no wall, no boundary where the universe ends. Instead, it is a limit imposed by causality. Beyond a certain distance, events have not had time to influence us. They exist, but their signals remain in transit or are being carried away by expansion faster than light can overcome. The light year is the unit that makes this comprehensible. It allows astronomers to translate cosmic age into spatial reach. It explains why the observable universe is larger than the universe's age multiplied by the speed of light, and why that reach is finite. Within this horizon lies everything ever directly observed. All galaxies, stars, nebulae, and cosmic structures detected so far exist inside this light-defined boundary. Outside it may lie more of the same, or something entirely different. The laws of physics give no reason to expect a sudden change. Yet without light, there is no evidence. This creates a subtle but important distinction between reality and observability. The universe does not end where observation stops. Human knowledge does. The light year draws that line with precision and indifference. The observable universe also changes how scale is perceived. Structures that once seemed unimaginably large become small in context. Superclusters spanning hundreds of millions of light years are revealed as filaments within an even greater web. Voids that appear vast are shown to be cavities within that structure. At the largest scales, matter is arranged like foam or sponge, with filaments and walls surrounding enormous empty regions. This pattern emerged from tiny fluctuations in the early universe, amplified by gravity over billions of years. The light year allows these patterns to be mapped, turning chaos into structure. Observing these patterns required surveying immense volumes of space. Galaxy surveys catalog millions of galaxies, each placed in three-dimensional space using distance estimates in light years. From this data, the architecture of the universe emerges statistically, not from individual objects, but from collective arrangement. The observable universe also reveals uniformity. On the largest scales, matter appears evenly distributed. No direction is special. No region is privileged. This homogeneity supports the idea that the universe is governed by the same laws everywhere. This uniformity is not obvious at smaller scales, where galaxies cluster and voids dominate. But when viewed across billions of light years, irregularities average out. The light year enables this perspective shift, allowing astronomers to zoom out until patterns stabilize. The existence of an observable horizon also reframes cosmic beginnings. Looking far enough away means looking back toward the era when galaxies were just forming. Beyond that lies the cosmic microwave background, the oldest light that can be observed. This radiation marks the moment when the universe cooled enough for atoms to form and light to travel freely. Before that, the universe was opaque. Photons scattered constantly, unable to move far. The light year loses meaning beyond this point because light itself could not propagate freely. The cosmic microwave background arrives from all directions, nearly uniform, with tiny fluctuations encoding the seeds of all later structure. Its light has traveled for nearly the entire age of the universe, stretched by expansion from intense heat into faint microwave wavelengths. Here, the light year intersects with origin. The distance that light traveled corresponds almost exactly to the age of the universe. It represents the longest journey any signal can have completed. Beyond this lies an era that cannot be seen directly. The universe before transparency exists only through indirect evidence, inferred from patterns imprinted on the microwave background and from theoretical models tested against observation. The observable universe, then, is not just a spatial boundary. It is a temporal one. It separates eras that can be seen from eras that must be reconstructed. This separation shapes how cosmology proceeds. Observations fill in the accessible region. Theory extends beyond it, constrained by consistency and physical law. The light year defines where one ends and the other begins. There is also a future horizon. As expansion accelerates, regions currently observable may slip beyond reach. Light emitted from those regions in the future will never arrive. The observable universe can shrink in practice even as time passes. This means that the present epoch is special in a quiet way. There are observations possible now that will not be possible later. There are galaxies visible today whose future light will never reach Earth. Knowledge has a temporal window. The light year captures this fleeting opportunity. It turns observation into something time-sensitive on cosmic scales. What can be known depends not only on where one looks, but when. The observable universe also challenges human intuition about completeness. It is tempting to imagine that what can be seen is representative of all that exists. Yet physics offers no guarantee of this. The universe beyond the horizon may be similar, or it may differ in ways that cannot be tested. This uncertainty is not a flaw. It is an honest consequence of the limits imposed by light and time. The light year enforces humility, reminding observers that access does not equal totality. At the same time, the observable universe is vast beyond comprehension. It contains hundreds of billions of galaxies, each with billions of stars. Even within this limited region, the amount of information available is overwhelming. The light year allows this immensity to be organized. It gives scale to abundance. It transforms overwhelming quantity into structured knowledge. Every map of the observable universe, every simulation, every model relies on distances measured in light years. Without this unit, cosmic cartography would collapse under its own numbers. The observable universe is not something that can be reached, crossed, or left behind. It is a relationship between time, expansion, and light. It exists because the universe has an age and light has a speed. This makes it fundamentally different from boundaries encountered in everyday life. It cannot be crossed by travel. It can only be expanded by waiting, and even that expansion is limited. The light year thus becomes a measure of cosmic patience. It defines what has already arrived and what remains forever beyond contact. It tells which stories the universe has already told and which will remain unheard. Within this horizon, everything that has ever been observed resides. Beyond it lies possibility without evidence. The distinction is clear, precise, and unavoidable. Understanding the observable universe clarifies the role of distance in cosmology. Distance is not merely about separation. It is about causality, accessibility, and the flow of information across time. The light year ties these ideas together. It transforms the universe from an abstract infinity into a knowable, bounded system shaped by physical law. As understanding deepens, attention naturally turns to the question of limits themselves. Not just what can be seen, but what cannot. Not just distance, but the boundaries imposed by physics on observation, communication, and influence. Those limits, and the role the light year plays in defining them, reveal as much about the universe as any observation ever could. Light years and cosmic evolution. Once distance becomes inseparable from time, the universe can no longer be understood as a static arrangement of objects. Every star, every galaxy, every structure exists within a process unfolding across light years and epochs. Cosmic evolution is not something inferred from theory alone. It is observed directly, written into the delayed arrival of light. At small distances, change is subtle. Nearby stars appear steady, long-lived, and predictable. Their evolution unfolds slowly, often beyond the span of human observation. At greater distances, however, change accelerates. Not because physics behaves differently, but because observation shifts backward along the timeline of the universe. The light year transforms the sky into a cross-section of development. Different regions reveal different stages of cosmic history, all visible at once. Nearby space shows maturity. Distant space shows youth. The farther the gaze, the earlier the stage. This effect allows astronomers to reconstruct how complexity emerged. Early in the universe's history, matter was distributed more evenly. Gravity had not yet had time to sculpt large structures. Galaxies were smaller, more chaotic, and more active. Star formation occurred at furious rates. Collisions were common. Light from those eras has traveled billions of light years to arrive. By the time it reaches Earth, the universe has changed profoundly. Galaxies have grown, structures have stabilized, star formation has slowed. Yet the evidence of those earlier conditions remains preserved in the arriving light. This preservation is not perfect. Light interacts with matter along the way. It is absorbed, scattered, and stretched. But enough information survives to reveal patterns. Astronomers compare populations of galaxies at different distances to trace how shapes, sizes, and behaviors change over time. The light year provides the timeline for this comparison. Without it, distant galaxies would simply appear different. With it, they become ancestors. One of the clearest examples of cosmic evolution revealed through distance is the rate of star formation. Observations show that the universe formed stars much more rapidly in the past than it does today. At distances corresponding to several billion light years, galaxies blaze with young, massive stars. Closer galaxies appear calmer, dominated by older stellar populations. This decline is not abrupt. It unfolds gradually across light years, revealing a universe that has aged, cooled, and settled. Gas reservoirs have been depleted. Collisions have become less frequent. The cosmic environment has changed. The light year also reveals how galaxies assemble. Early galaxies were often irregular and fragmented. Over time, they merged and accreted material, forming larger systems. Spiral arms emerged. Elliptical galaxies formed through violent collisions. Each stage is visible at different distances. This observational sequence confirms models of hierarchical structure formation. Small structures form first. Larger ones grow through accumulation. The universe builds complexity step by step, guided by gravity and constrained by expansion. Distance also reveals the evolution of elements. The early universe contained mostly hydrogen and helium. Heavier elements formed inside stars and were spread through supernova explosions. The farther back astronomers look, the fewer heavy elements they find. Light years become markers of chemical enrichment. This matters deeply. Planets, life, and technology depend on heavy elements. Their abundance increases over time. Observing galaxies at different distances reveals when the ingredients for complexity became widespread. The light year thus connects cosmic evolution to the conditions necessary for life. It shows that there was a time when the universe lacked the materials needed for planets like Earth. It also shows how those materials gradually accumulated. Even the cosmic background radiation fits into this evolutionary picture. It represents the universe at a time when it was hot, dense, and nearly uniform. Its light has traveled across nearly the entire age of the universe. It marks the earliest stage that can be observed directly. Between that early glow and the structured universe seen nearby lies a vast evolutionary arc. Light years divide that arc into observable segments, each revealing a different phase. Cosmic evolution is not smooth. It is punctuated by transitions. The first stars ignite. The first galaxies form. The universe becomes transparent to certain wavelengths. Each transition leaves an imprint in the light that follows. Distance allows these imprints to be separated and studied. Without delay, all eras would collapse into a single view. With delay, history unfolds spatially. The light year also clarifies the pace of evolution. Some processes are rapid. Supernova explosions occur in moments. Others are slow. Galaxy formation spans billions of years. Distance stretches these timescales into something observable. This perspective reveals that change is relative. A star's life may seem long, but compared to the age of the universe, it is brief. A galaxy's lifetime may seem eternal, but compared to the future of cosmic expansion, it is transient. The universe evolves not toward a goal, but along a trajectory shaped by initial conditions and physical laws. Light years record that trajectory without interpretation. They preserve what happened, not why it happened. As expansion continues, cosmic evolution also changes direction. Star formation declines, galaxies age, energy density shifts, dark energy becomes dominant. The future universe will look different from the past in ways that distance will eventually reveal. Yet there are limits to this observation. As discussed earlier, accelerated expansion will eventually hide much of cosmic history from view. Light years that once delivered information will no longer do so. Evolution will continue, but its record will thin. This makes present observations uniquely valuable. They capture a universe in mid-transition, rich in structure and diversity. They preserve a wide range of evolutionary stages at once. The light year, in this sense, acts like a window of coincidence. It aligns the arrival of light from many eras into a single moment of observation. This alignment will not last indefinitely. Understanding cosmic evolution through light years also reframes humanity's place in time. Earth formed relatively late in cosmic history. The conditions that allowed life to arise were products of billions of years of stellar evolution. Distance reveals this lineage. The atoms in the human body were forged in stars whose light may still be traveling through space. Cosmic history is not abstract. It is embodied. The study of cosmic evolution is therefore not detached. It connects present existence to past processes unfolding across light years. It reveals that complexity emerges gradually, not suddenly. The light year makes this emergence visible. It turns time into distance and distance into story. As this understanding deepens, attention naturally shifts toward the limits of this story. How far can cosmic evolution be traced? What happens when observation runs out and only theory remains? Those questions lead to the boundaries of measurement, where the light year still defines distance, but evidence grows thin and uncertainty grows large. The universe, revealed through light years, is not just vast. It is dynamic, historical, and unfinished. Its evolution continues, shaped by the same principles that governed its earliest moments. Distance allows that continuity to be seen. The light year is the scale on which cosmic change becomes legible. In tracing cosmic evolution, the light year becomes more than a unit. It becomes a narrative frame, within which the universe's past, present, and future can be understood as parts of a single unfolding process. The limits of communication. As distance unfolds into time and time into history, another consequence of the light year becomes unavoidable. The universe is not only vast in scale, it is fragmented in communication. Information does not flow freely across all of space. It moves at a fixed speed, constrained by the same limits that define observation. The light year, which measures how far light can travel in a given time, also defines how far influence can reach. Communication, in the most fundamental sense, depends on the transmission of information. In the universe, all such transmission is bound by the speed of light. No signal, no matter how advanced its source, can arrive faster. This rule is not a technological limitation. It is a property of space-time itself. At human scales, this constraint is barely noticeable. Messages cross continents in fractions of a second. Signals bounce between Earth and satellites almost instantly. Even communication with distant spacecraft within the solar system, though delayed, remains manageable. Once communication extends beyond the solar system, the character of delay changes completely. A signal sent to the nearest star system would take more than 4 years to arrive. Any reply would take another 4. Even the simplest exchange would span nearly a decade. The light year makes this delay explicit. It transforms communication from conversation into correspondence, where time becomes an inseparable part of the message. At galactic scales, communication becomes effectively impossible in any practical sense. Signals sent across the Milky Way would require tens of thousands of years to arrive. Civilizations could rise and fall during the transmission of a single message. The light year enforces isolation not by hostility, but by scale. This isolation deepens beyond galaxies. Communication between galaxies would require millions or billions of years. Any exchange would be disconnected from the lifetimes of civilizations, species, or even stars. The universe is not silent because nothing speaks. It is silent because distance stretches response beyond relevance. The light year also limits influence. Events cannot affect regions beyond their light travel horizon. A supernova may devastate nearby systems, but its effects fade with distance. Beyond a certain number of light years, only light arrives, and even that arrives diluted and delayed. This separation creates independent regions of causality. Each region evolves largely on its own, shaped by local conditions. The universe becomes a mosaic of loosely connected domains, each bounded by the reach of light. These domains are not static. As time passes, their boundaries shift. Expansion carries regions apart, horizons form, connections weaken. The future universe will consist of increasingly isolated islands, each defined by what light can still cross. The limits of communication also shape scientific understanding. Knowledge of the universe depends on passive reception of signals. Astronomers cannot experiment on distant galaxies. They cannot probe them directly. They must interpret what arrives, delayed and filtered by distance. This constraint demands caution. Observations represent past states. Models must account for delay. Conclusions must acknowledge uncertainty introduced by time separation. The light year enforces epistemic humility. Yet within these limits lies remarkable coherence. Despite immense separation, physical laws appear consistent everywhere observed. Light behaves the same regardless of its origin. Spectral lines match laboratory measurements. Constants remain constant across billions of light years. This consistency allows inference. Even without communication, comparison becomes possible. The universe can be understood as a system governed by uniform principles revealed through delayed signals. The light year also reframes the search for intelligence beyond Earth. Any potential signals from other civilizations would be subject to the same delays. A detected signal would represent a message from the past. The sender may no longer exist. The context may be irretrievable. This does not diminish the significance of such a discovery. It clarifies its meaning. Communication across light years is not dialogue. It is archaeology. The absence of detected signals, often framed as silence, must be interpreted through the lens of distance. The universe is not small enough for conversation. It is only large enough for traces. These traces need not be deliberate. Technological activity leaves signatures: radio emissions, atmospheric changes, infrared excess. Each would be observable only if it occurred within a reachable light-year radius and within the appropriate time window. Again, the light year defines possibility. Beyond certain distances or times, evidence fades beyond detection. Communication limits also apply inward. Even within a galaxy, coordination across regions is impractical. Galactic civilizations, if they exist, would be isolated by time. Shared culture across tens of thousands of light years would be impossible to maintain. This fragmentation challenges intuitive notions of universality. The universe is not a single, shared environment. It is a patchwork of local realities, each unfolding according to its own clock. The light year formalizes this fragmentation. It shows that simultaneity is local. There is no cosmic present. Each region experiences now differently, and those differences are insurmountable. This does not imply disorder. On the contrary, the universe exhibits large-scale regularity precisely because local processes dominate. Regions evolve independently, yet according to the same laws. The limits of communication also protect complexity. Without constant external interference, systems can develop stability. Stars live out their lives. Galaxies evolve gradually. Planets maintain long-term conditions. Distance becomes a buffer. The light year enforces separation that allows order to persist. At the same time, this separation means that no observer can ever grasp the universe as a whole. Knowledge is necessarily partial. It is assembled from fragments delivered by light across time. This does not weaken scientific understanding. It defines its scope. Science becomes the study of what can be known given the constraints imposed by light years and expansion. Within those constraints, extraordinary precision is possible. Measurements of distant galaxies reveal parameters of cosmic expansion. Observations of ancient light test theories of fundamental physics. The universe, though fragmented, remains legible. The light year is central to this legibility. It provides a consistent scale across which delay, distance, and causality can be reconciled. The limits of communication also sharpen philosophical questions. If regions of the universe can never influence one another, in what sense do they share a single reality? The answer lies in shared origin and shared law. All regions emerge from the same early conditions. All obey the same physical rules. Distance separates, but it does not sever common heritage. Understanding these limits prepares the ground for deeper questions about measurement itself. How do units like the light year arise? Could other measures replace it? Or is it uniquely tied to the structure of the universe? These questions turn attention inward, toward the tools of understanding rather than the objects understood. The light year, so familiar and yet so profound, invites examination of its own necessity. It is not merely a convention. It is an expression of how the universe allows itself to be known. The limits of communication do not end inquiry. They frame it. They define where knowledge can reach and where it must stop. The light year stands at that boundary, marking both reach and restraint, possibility and impossibility. In doing so, it reveals a universe that is not silent, but patient, speaking slowly across distances measured not in words, but in years of light. Could anything replace the light year? As understanding deepens, it becomes natural to question the tools used to describe it. The light year feels intuitive now, almost inevitable, yet it is a human construct built from two familiar quantities: time and the speed of light. This raises an important question. Is the light year simply convenient? Or is it uniquely suited to describing the universe? Could some other measure replace it? Or does the structure of reality itself demand a unit like this? At first glance, alternatives seem plausible. Astronomers already use other units. The astronomical unit measures the average distance between Earth and the Sun. The parsec, derived from parallax geometry, is widely used in professional astronomy. Kilometers and meters remain fundamental in physics. Each of these units has value, yet none fulfills the same role as the light year. The key difference lies not in scale, but in meaning. A kilometer measures separation without context. It says nothing about time, delay, or causality. An astronomical unit extends that scale outward, but remains tied to a single planetary system. Even the parsec, though powerful, is still fundamentally geometric. It describes distance, but not experience. The light year does something different. It embeds time directly into distance. It transforms separation into delay, geography into history. This is not an aesthetic choice. It reflects how the universe actually behaves. Because information cannot travel faster than light, distance and time are inseparable at cosmic scales. Any unit that ignores this relationship is incomplete. The light year captures it explicitly, making delay unavoidable in interpretation. Consider communication. A signal sent across 1 light year will arrive in 1 year. This is not a convention. It is a physical necessity. No alternative unit can remove that delay. The light year simply states it plainly. This is why replacing the light year would not eliminate its implications. One could express distances in meters or parsecs, but the same questions would return. How long did the light take to arrive? How old is the information? What era is being observed? The light year answers these questions automatically. Even the parsec, widely favored by astronomers, does not escape this logic. A parsec corresponds to about 3.26 light years. Professionals may prefer it for historical and mathematical reasons, but they still translate it mentally into light years when considering observation and delay. This reveals something important. The light year is not just a unit. It is a conceptual bridge. It connects measurement to meaning. Could a civilization elsewhere develop a different unit? Almost certainly. They might define distance using their own orbital periods or spatial references. Yet once they discover that light has a finite speed, and once they begin observing distant objects, they would confront the same relationship between distance and time. They would realize that to see farther is to see earlier. They would need a way to express that link. Whether they call it a light year or something else, the concept would emerge inevitably. This suggests that the light year is not arbitrary. It is an expression of space-time structure. It arises naturally from 2 facts. Light has a constant speed, and the universe is vast. Even in theoretical physics, where abstract units are common, the speed of light plays a central role. It links space and time into a single framework. Distances can be converted into times and vice versa. The light year sits comfortably within this framework, translating theory into intuition. In relativistic terms, distance without time is incomplete. Events are defined by space-time intervals, not by spatial separation alone. The light year, while not a relativistic unit in the strict sense, gestures toward this deeper unity. It also serves communication. For non-specialists, the light year conveys meaning immediately. Saying that a galaxy is 10 billion light years away communicates both distance and age. It tells the listener that the light has traveled for 10 billion years. No further explanation is needed. This clarity matters. Science advances not only through discovery, but through understanding. Units that obscure meaning hinder that process. The light year enhances it. There have been attempts to replace or supplement the light year with other measures. Cosmologists use comoving distance, proper distance, and look-back time, each describing a different aspect of separation in an expanding universe. These are powerful tools, but they are context-dependent. They require explanation. The light year remains the common denominator. It is the unit to which others are compared. It anchors abstract measures to something physically grounded. Even when discussing horizons and unreachable regions, the light year remains central. Horizons are described in terms of how many light years away they lie, how long light has traveled, and whether it ever will arrive. The language of light persists. This persistence reflects necessity rather than tradition. The universe communicates through light. Understanding that communication requires measuring light's journey. The light year also shapes imagination. It helps the mind accept scales otherwise beyond comprehension. Billions of kilometers blur into abstraction. Billions of years evoke narrative. The light year unites the two. Could a unit based on gravity replace it? Gravity propagates at the speed of light as well. Could a unit based on cosmic expansion serve instead? Expansion is measured through redshift, which itself depends on light. Every candidate returns to the same foundation. This circularity reveals a deeper truth. Light is not just a messenger. It is woven into the fabric of space-time. Any attempt to describe the universe at large scales must contend with its role. The light year also reminds observers of limitation. It carries an implicit warning. You are seeing the past. You are separated by time. Certainty fades with distance. No other unit delivers this message so clearly. Replacing the light year would risk losing that caution. It might encourage thinking of distance as something static and conquerable, rather than something that enforces delay and isolation. In this sense, the light year performs an ethical function within science. It resists simplification. It refuses to let distance be treated casually. It insists on patience. The universe rewards that patience with understanding. Those who wait for light receive information that cannot be obtained any other way. Those who ignore delay misinterpret what they see. As observation grows more precise and reaches farther, the light year becomes even more essential. The distances involved grow so large that delay dominates interpretation. The unit that encodes that delay becomes indispensable. Thus, the light year is unlikely to be replaced. It may be supplemented, refined, or contextualized, but its core role will remain. It aligns with how the universe actually behaves, not just how humans prefer to measure. The question of replacement reveals something deeper. The light year is not chosen because it is convenient. It is chosen because it is honest. It tells the truth about separation. It tells the truth about time. It tells the truth about what it means to observe a universe governed by finite speed and vast scale. In doing so, it anchors understanding in reality rather than abstraction. As inquiry moves toward its final perspective, attention shifts from measurement and limitation to meaning itself. What does it imply to live in a universe where distance is time, where observation is memory, and where light years define both reach and restraint? Those implications extend beyond astronomy. They shape how existence itself is understood within a cosmos defined by delay, separation, and continuity. The light year, having guided measurement, now guides reflection. What the universe looks like in light time. By the time distance has been translated into time and time into limitation, the universe no longer appears as a simple arrangement of objects scattered through space. It becomes something more layered and more complex. What is visible at any moment is not a snapshot, but a composite image assembled from different eras, each carried to the present by light traveling across different lengths of time. This means that the universe, as observed, is never synchronized. Nearby stars appear almost contemporary. Their light left them recently, on cosmic timescales. More distant stars belong to earlier moments. Galaxies billions of light years away are seen as they were when the universe was young. All of these views arrive together, forming a single image that never existed as a unified moment anywhere. The night sky, then, is not a picture of now. It is a collage of then. Understanding this reshapes perception. When looking outward, one is not surveying a single state of reality. One is sampling multiple stages of cosmic history at once. Distance distributes time across the sky, and light stitches those times together into something observable. This effect becomes more pronounced the farther observation reaches. A deep astronomical image may include stars within the Milky Way, nearby galaxies, distant clusters, and extremely remote galaxies near the edge of the observable universe. Each of these objects belongs to a different epoch. Their light has traveled for years, millions of years, or billions of years before arriving at the same detector. The resulting image is temporally stratified. It is accurate but not simultaneous. Light time, rather than space alone, determines what is seen. Objects closer in light time appear more evolved. Objects farther in light time appear more primitive. The universe presents itself as a developmental gradient rather than a uniform field. This gradient allows astronomers to study change without waiting. Processes that take billions of years can be observed across distance. Evolution becomes spatially distributed. The universe performs its own time-lapse, visible through light years. Yet this also introduces complexity. Two objects separated by distance may not be comparable in simple ways. A nearby galaxy and a distant galaxy are not just far apart. They are separated by developmental stage. Comparing them requires accounting for age as well as structure. The light year provides that accounting. It tells how much time separates the observed state from the present. It allows correction for evolution, helping astronomers distinguish between intrinsic differences and temporal ones. This is why surveys of the universe often group objects by redshift or distance. Objects seen at similar light times are compared to reconstruct typical conditions of that era. From these comparisons, trends emerge. These trends reveal that the universe has directionality. It changes in consistent ways over time. Galaxies grow. Star formation peaks and declines. Structures assemble. Energy density shifts. None of this is apparent from a single object. It becomes visible only when distance distributes time across observation. Light time also explains why the universe looks different at different wavelengths. Early stars emit strongly in ultraviolet light. As their light travels and the universe expands, it is stretched into visible and infrared wavelengths. Observing different wavelengths is equivalent to observing different eras. The universe, therefore, cannot be understood through one window alone. It must be viewed across the electromagnetic spectrum. Each band reveals light from different stages of cosmic history. Light time also affects apparent motion. Some distant galaxies appear frozen, their changes imperceptible. Others, closer in light time, show variability. This is not because distant galaxies are static, but because their changes are spread across timescales much longer than human observation. Even dramatic events like supernovae become rare in distant galaxies simply because of time dilation and observational limits. Their light arrives stretched and faint, making detection difficult. The The universe in light-time is not only layered, it is filtered. Some events are visible, others are not. Distance determines not just delay, but detectability. This filtering introduces bias. The universe observed is not a complete representation of all that exists or all that happens. It is a selection shaped by distance, brightness, wavelength, and time. Recognizing this bias is essential. Without it, conclusions would be skewed. Astronomers must constantly correct for what cannot be seen, as well as what can. The light year provides the framework for these corrections. It allows estimation of how many objects lie beyond detection and how representative observed samples truly are. Light time also reframes the idea of simultaneity. In everyday life, simultaneity feels absolute. Two events happen at the same time or they do not. In the universe, simultaneity dissolves beyond local scales. Events separated by light years cannot be said to occur at the same moment in any operational sense. There is no universal clock that synchronizes distant regions. Each region has its own local present. The universe seen in light time is therefore fundamentally asynchronous. What appears together did not happen together. What happens together may never appear together. This asynchrony is not a flaw. It is a feature of space-time. It allows the universe to be observed at all. If light arrived instantly, distance would be invisible and history inaccessible. Light time turns separation into knowledge. It also introduces irreversibility. Once light has passed, that particular view of the universe is gone. It cannot be retrieved or repeated. Observations capture unique moments in cosmic history. This uniqueness gives astronomical data a special character. It cannot be replicated under controlled conditions. Each observation is a one-time event, preserved only through records and analysis. The universe in light time is therefore both generous and fleeting. It offers vast information, but only once. This perspective also alters the meaning of present observation. Observers are always late. They never see events as they happen. They see them after the fact, sometimes long after. Yet this lateness does not diminish truth. It defines it. The truth of the universe is not bound to immediacy. It is bound to consistency across delay. The light year ensures that consistency. It allows comparison across time, revealing laws that hold despite separation. Light time also gives the universe a kind of depth that cannot be flattened. Distance cannot be collapsed into a single moment without losing information. The universe resists simplification. In this resistance lies its richness. The universe is not a static object. It is a process unfolding across time, visible only through the patience of light. Understanding what the universe looks like in light time prepares the ground for a final perspective. Distance, time, limitation, and evolution converge into a single realization about how humans exist within this vast system. The light year has guided measurement, framed observation, and revealed limits. What remains is to understand what it means to inhabit a universe defined this way. That meaning does not lie in numbers alone. It lies in perspective, distance, time, and meaning. When the light year is followed to its furthest implications, it stops being a technical term and becomes a lens through which existence itself is viewed. Distance is no longer just separation. Time is no longer just duration. Together, they define how reality is revealed, how knowledge is acquired, and how meaning is constructed within a universe that cannot be grasped all at once. To live in a universe measured in light years is to live in a universe where immediacy is rare. Nothing distant is ever encountered directly. Everything beyond the local is known through delay. The present, as experienced, is always partial. What appears stable may already have changed. What seems permanent may no longer exist. This does not render knowledge fragile. It renders it contextual. The light year teaches that certainty does not require simultaneity. Truth does not depend on immediacy. Laws of nature remain consistent even when their evidence arrives late. The universe behaves reliably across separation. And that reliability is what makes understanding possible at all. Distance measured in light years also removes the illusion of centrality. No location occupies a privileged position. Every observer exists within a local bubble of causality, bounded by what light can reach. From any point in the universe, the same constraints apply. Horizons form, delays persist, perspective remains limited. This universality matters. It means that the universe does not favor viewpoint. It offers no master frame from which everything can be seen at once. Knowledge is always local, assembled from signals that have survived the journey. The light year enforces this humility. It resists the idea that scale can be conquered simply by better tools. Instruments can grow more sensitive, but they cannot outrun light. Patience cannot be bypassed. At the same time, the light year reveals something quietly extraordinary. Despite these constraints, the universe is still intelligible. Patterns persist across distance. Structures repeat. Laws hold. Light arriving from billions of years ago behaves exactly as predicted by physics tested in laboratories today. This consistency across time and distance is not guaranteed. It is discovered, and it is one of the most profound facts about reality. The universe, though vast and fragmented by light years, is coherent. This coherence allows the past to inform the present. Ancient light reveals early conditions. Distant galaxies reveal how structure formed. Cosmic background radiation reveals the universe at its earliest observable moment. All of this information arrives late, but it arrives intact enough to be understood. Distance becomes not an obstacle, but a resource. It spreads time across space, making history observable. The light year also reframes human significance. In a universe billions of light years across, individual lifetimes are vanishingly brief. Civilizations flicker. Even species are temporary. Yet through observation, minds can reach across time far exceeding their own duration. This reach is not physical, it is cognitive. It exists because light carries information and because intelligence can interpret it. Meaning emerges not from scale, but from connection. A photon emitted billions of years ago finds an eye, a detector, a sensor capable of understanding what it carries. Across the void, a relationship is formed. The universe does not know it is being observed. Yet observation matters. It transforms raw signal into knowledge. It turns distance into understanding. The light year makes this transformation visible. It shows that knowledge is always delayed, always partial, yet still powerful. There is also a quiet symmetry in this arrangement. Just as distant regions cannot see us immediately, we cannot see them immediately. Every observer is equally constrained. The universe is fair in its limits. These limits shape destiny. In the far future, expansion will isolate regions permanently. Galaxies will fade. Light will thin. Observers may one day see a quieter sky, unaware of the vast structures that once lay beyond reach. Yet even then, the light year will still describe reality. It will still define what can be known and what cannot. The universe will remain governed by the same principles, even if fewer signals arrive. This suggests that meaning in the universe is not tied to abundance of information, but to interpretation of what is available. The light year does not promise completeness. It promises structure. Within that structure, inquiry finds its place. Questions are shaped by distance. Answers arrive through time. Understanding grows incrementally. The universe revealed through light years is not an instant revelation. It is a long conversation conducted across billions of years, one photon at a time. To participate in that conversation is to accept delay without frustration, uncertainty without despair, and limitation without defeat. It is to recognize that knowledge is not diminished by patience, but defined by it. Distance also protects diversity. Regions evolve independently. Conditions vary. Outcomes differ. The universe does not collapse into uniformity. It unfolds into variety. The light year, by enforcing separation, allows this richness to exist. In this sense, distance is not the opposite of connection. It is the condition that makes meaningful connection possible. Without distance, there would be no history. Without delay, no archive. Without light years, no cosmic story. The universe does not rush to reveal itself. It unfolds at a pace set by its own laws. Light travels, space expands, time passes. Understanding arises when these elements are allowed to do what they do. The light year stands at the intersection of these forces. It is not merely a measurement. It is a reminder of how reality presents itself. It tells that seeing is remembering, that observation is reception, that knowledge is never instantaneous. And yet, across all this separation, the universe remains comprehensible. That is the final, quiet revelation. A universe measured in light years is a universe that allows itself to be known, slowly, partially, and truthfully. Distance does not erase meaning. It gives it depth. Time does not weaken understanding. It shapes it. And the light year, carrying both distance and time in a single expression, reveals a cosmos where limitation and knowledge coexist, not in conflict, but in balance. The light year is often described as a number, a distance too large to imagine, a scale too vast to feel. But by now, it has become something else. It has become a reminder that the universe is not experienced all at once, that everything beyond the immediate is known through patience, that to look outward is to look backward, not by choice, but by necessity. Every star in the sky is already a memory. Every galaxy is a message sent long before it was received. And every image of the universe is a record of moments that no longer exist in the same form. Distance does not hide the universe. It reveals how it unfolds. The light year shows that reality is layered, not distant. That time is not separate from space, but woven into it. And that understanding does not come from arriving faster, but from waiting long enough to see what arrives. In a universe measured this way, certainty is never immediate. Knowledge is earned through delay. And perspective grows not by shrinking the cosmos, but by accepting its scale. What we observe is not the universe as it is now, but the universe as it has been, carefully preserved by light traveling across expanding space. And somehow, across billions of years, that light still finds us. It finds instruments built from matter forged in stars. It finds minds capable of interpretation. It finds curiosity. The universe does not announce itself. It does not rush to be understood. it simply continues, sending its story outward at the only speed it knows. The light year is how that story reaches us. If this journey through distance and time has changed how you see the night sky, or made the universe feel deeper rather than farther, you're welcome to continue exploring these ideas here. Not to arrive at answers quickly, but to let understanding build the way the universe does, slowly, patiently, and across light years.